Thank you. First, thank the organizers for the invitation and the first time visit the Institute and the second time in Austria, last time in Linz with a bad experience. If you want to know, I can tell you later. But this time is so far so good and everything's good. And again, thank you. Thanks for the organizers for this invitation, also opportunity to visit here and see good older friends, also meet some new friends. I'm the know a lot of wave people, but the kinetic people is the first time to this community. Even I have a colleague, Corey Hawk, he's working in this area. Okay, so because the title is related wave, actually the material is for the random PDE, okay, in general. So let me start with the acknowledge my collaborators and June Xiaolin from Auburn University, former student Cody Lawton, and now he goes to the industry, not in the university anymore. And also the later collaborators, David Nichols for the University of Illinois Chicago on the wave scattering. And the current student, he just finished and go with work the postdoc with David and in August, and another professor from the South Carolina. So because for this community, you don't need too much introduction, but I just mention some terminologies. The main part will be this one and this one, and also to motivate the generalized method I mentioned about the ensemble method I learned from him. Okay, so we start with the terminology because we saw a lot of the UQ here. Same so far, most people talk about the random PDE. The random PDEs, the coefficients, source terms are random with the randomness. Actually, that's one motivation. We are doing too, but lately, last 5 years, in collaboration with the older friend Andreas Pro from Tübingen, which is my next stop after Vienna. So we have been doing the solving the stochastic nonlinear PDEs, which is driven by some stochastic process. Here you can think this is the simplest case is Hilbert space value, the linear process. You can make it more fancier, like the wave process, even any semi-martingale in the Hilbert space value. For us, we are more interested in the nonlinear PDEs, like the stocks, number stocks, and stochastic Schrodinger, nonlinear Schrodinger is the right place to mention the Schrodinger, okay? And also for the stochastic phase field, like in particular Allen-Kaka-Hilliard type equations, driven, of course, here, mostly driven by the so-called Q linear process. And lately, we've just finished work with the Andreas group on the stochastic nonlinear wave equation, which is a second order in time. The U should be replaced by the V sub T. So you have a second derivative in time. Okay. But each of these are another talk. So I just motivate why we do what I'm going to talk. Okay. So one thing I want to mention is that I learned from almost 10 years ago from a workshop in IMA, Minnesota, a talk given by Papa Nicola. He was mentioning is for the high frequency wave problems. If you do this, adaptation, in particular for the stochastic Galerkin method, it doesn't work well. And you can look at his webpage, and I think he still have older slides. So if in particular for high wave, high wave number wave problems, it doesn't work well for stochastic Galerkin unless you do something, modification. So basically, be careful for some problems; those don't work well. The other thing for this community, everybody knows, we compute not only solving the random PDE or stochastic PDE. We are computing the quantity of stochastic interest. So not only solution itself, but also that's what we want to compute. Okay. So for the PDEs, and you can discretize using the standard. You can try deterministic techniques in time, in space. Actually, most of them it works to some extent. Analysis is completely different, but in terms of the practical computation, it works to some extent. But be careful, some doesn't work. For example, I don't have time to talk about this, like the stocks and the stocks, numerical stocks. If you do the mixed method, it doesn't work well. Standard mixed method doesn't work well. You have to do something different, okay? But you can try. Always a deterministic method you can try for solving stochastic PDEs. Okay. So here, this talk focuses on the, so we discretize time, discretize space using the standard way or modified way. So that is another talk, the F is this talk. This talk is about how to discretize in a stochastic variable, omega variable. So that is the focus of this talk. Okay. So we saw a lot of methods already in this talk, in this workshop so far. I summarize in a different way. So I call it either the sampling method. You can have all kinds of Monte Carlo type. I call the sampling method. The other one is non-sampling method, like the stochastic Galerkin or polynomial chaos. You don't do the sampling. Okay. So that is my understanding. So what I'm going to talk later is focus on the sampling method, how to make a sampling method more efficient. So actually, I already said it here earlier. So for the high frequency waves, if you do the standard way, it doesn't work well. And there are counterexamples that don't work well. And for the stochastic PDEs, if you discretize in time, for example, using the simplest method called the Euler-Maruyama method, essentially back with Euler, you discretize in time first, then you can see in each time step, you have the random PDE. So you convert the stochastic PDE into a random PDE in each time step. So all the techniques for solving the random PDEs can be applied. So that's in a sense, so the solving numerical method for solving random PDEs is a coarse grid building blocks for solving a stochastic PDE. Okay. So here is this is the if you think about the Wiener process, you have to discretize this using the left point. Otherwise, and there is there's a measurability issues. Okay. You can also do some more like the Stratonovich type, but that don't go that deep over there. So anyway, if you discretize in time, each time step, you get the random PDE. You convert the stochastic PDE into random PDE, then you have to solve random PDE. So that is another motivation for we consider this kind. So below, in the remaining talk, I will focus on solving a random PDE, not a stochastic PDE. Okay. So focus on how to discretize in the stochastic variable omega, okay. Make it more efficient. Okay. So the method that we call the multi-mode Monte Carlo method is again the sampling method, just to make Monte Carlo method more efficient. It is a small trick. It's not just something, earth-shaking idea, just a small trick. So make the Monte Carlo, not using the brute force Monte Carlo, too expensive. And you think about it, so number of stocks hundreds of times, and maybe 1,000 times. That's a lot of work. So we want to make it more efficient. Okay. So the method is start with a simple case first. So definition for the weak random field. So you have the coefficient, think of the typical coefficient. Just think of the diffusion equation. A typical diffusion coefficient is called the weak random field. If this is you have the deterministic background and with a small random perturbation. So that's called the weak random field. So all the coefficient has this property called the weak random field. Okay. In this case, if you have a linear random PDE abstractly, okay, so then you can prove in general for the for diffusion equation for the wave problems, you can prove the solution has this small parameter epsilon expansion and the power series. Okay. So this is in the spirit of the homogenization, but it's different. It's different from homogenization, but in the spirit of in that direction. You can write a solution into the infinite series in power epsilon. Of course, in computation, you stop somewhere as approximation. In practice, we only need a capital N as very small. 3, 4, that's it. Okay. Interesting is you plug this into it, then you do this compare the powers of epsilon. You can see that each mode function, uj, satisfy the linear equation. And it's a recursive relationship. So equation is a recursive, one solve one based on the other. And this right-hand side, so the current mode, UJ depend on the previous modes, only very few, 2 or 3 in practice. You will see the little examples. So more importantly, what is this squared error? It's a linear operator, but it's a deterministic operator. That's interesting. The deterministic operator. So therefore, your left-hand side, your PDE operator now is a deterministic operator. All the noise goes to the right-hand side. So that is for the numeric people we know. That is the ideal setting to take advantage for the direct solver or block solver, like a block Krylov subspace method. So you can put all these for all the samples, put at the right-hand side at the matrix. If you do the block, okay. Or you can do the LU because this operator left-hand side is deterministic. You do the direct method. You sieve it. Then you reuse for all the modes, for all the realization. So that's where you do the sieving, okay, on the solver level. Okay. And then you can solve this linear PDE using any your favorite method to do discretization in space. Okay. So that is the basic idea. You have a sieving in the solver level. And the discretizations is, in some sense, the discretizations with the solvers tied together. When you discretize your problem, you think about the solver also beforehand. Okay. Otherwise, maybe too late. You cannot reuse computation. So summarize, very simple algorithm. So you discretize your first mode, the 0 mode, using your favorite space solver, discretization method. And later for the wave problem, we use DG. There's a good reason for that. Then you see with the matrix, the coefficient matrix, the Stephanie matrix, you get here I just present the direct solver case. You do the aerial, and you see with the aerial. That aerial will be repeated use for solving all the modes and all realizations. Then you do the backward substitution. Okay. So that is where the sieve comes from. Then you form your approximate solution. And then you have all the computation for all the realizations. Then you can compute the expectation, variance, whatever, high moments easily. Okay. Just because you have all the the realizations you see with there, you just form the quantity of stochastic interest. Okay. So that is a general algorithm. So the key part is you reuse the computation. That's how you make the sievings. Because in particular, when you solve the problem many times, many realizations, otherwise it's very, very expensive. That is a brute force Monte Carlo. So here is you see by reusing computation. Then error analysis is very simple. To the triangle inequality. You have this is your quantity of stochastic interest. This is the computed one. You do the triangle inequality, then your first part is the moment expansion approximation, should be powerful epsilon. And the next term, you use your favorite space discretization, and there should be error in powerful h. Okay? Then lastly, you do because it's a Monte Carlo type, and then you have the Monte Carlo error there. And each part you make it is optimal. That's if you follow this approach, that's in some sense the optimal method. Okay. Well, that is a simple case. That is a weak media case. How about the general media case? If your media is not nice like that. Okay. So how to generalize to the general case? The answer is partially yes. We can do for some type more general media, but not for every media. Okay. So the idea is very simple. You convert non-weak media into equivalently, write this into the weak media case. Okay. How to do that? If in a simple case, you can do this K-error expansion. If you have, in some case, I'll show you an example later, and you can do the K-error expansion to convert your media coefficient into the weak media coefficient. The other more sophisticated one is using technique borrowed from stochastic homogenization. That is more involved. We will not talk about this one. Actually, we also did a backward. Also later I mentioned about this, and using this technique backward solving the stochastic homogenization problem. Okay. The other idea is adapting the idea using the ensemble method, which we are introducing later. Okay. So how to do that? Example. If your media is a Gaussian type, and for the Gaussian type is uniquely determined by mean and the variance function. Okay. The covariance function, and in many applications, in particular in material science and geoscience, this covariance function has this exponential type, exponential decay, meaning it's a near neighbor interaction. You depend on distance in the near neighborhood. Okay, not the farthest. If the far field interaction, then this idea does not work. Okay, so it's a limitation. Okay, so in this case, you using this covariance function, you form a covariance operator. Covariance operator, it will be the self-adjoint operator, has a nice complete sequence of the eigenvalues, eigenfunctions. That is lambda k and phi k. So that is a famous K-error expansion. You find the Gaussian, every Gaussian can be expanded in this infinite series in terms of eigenvalues, eigenfunctions for the covariance operator. Okay? And the Cassis, that is the real valued sequence of real valued Brownian motion. Okay, so here's the key. And for that type, the C, the covariance function, can be proved the leading eigenvalue is in the order of the error, some power. What is the error? Error is, this is called the correlation length. That's important. It's usually small. In these applications, it's small. Okay. So, and for some algebra, you can put these leading eigenvalues in front with lambda 1 and divide by the rest. So this lambda 1 is the power, which is related to the error. It's small parameter, and we just give you epsilon. So you rewrite your Gaussian variable, the Gaussian, into this weak media form equivalently. Okay. Then using the framework I presented earlier, then you can do this general case. Okay. So this is the one example, and we reformulate. Okay. You can do more sophisticated one using the stochastic homogenization technique, reformulate your coefficient into the weak media case. Okay. And later I will show you how to do this using the ensemble method, combined with the ensemble method, which provide another way to do it. Okay. Okay, so that is for the framework. Just generally, abstractly, you have the random PDE, you do this, you have coefficient has the weak media form, do the expansion, then you do the modes, computer modes, and then you solve the modes efficiently. So that is the algorithm. Okay. So now look at the application. So here I just focus on one application because the rest is similar, which is a random acoustic wave equation, which is basically the Helmholtz equation. And we saw this several times in the last 2 days. So here is the randomness and the coefficient is density, the media. So this is the alpha is 1 over alpha square is 1 over rho. Okay. So the random media. Okay. And the K is wave number. And this is a simple case, which is the first order observed boundary condition if G equals 0. Okay. So in this case, first we consider you only need to consider a weak media case. For general media case, you have the reformulation, and then you apply the weak media case. Okay. So here we assume that this weak media case, alpha have this deterministic background with the random perturbation. Okay. So then, and what will be, first, for this problem, and for the wave community, people like to have this called wave number explicit stability estimate. Okay. So here, in the, using our older technique for using this called relative identity idea, we did it for the deterministic case, and it works also for the random case. Okay. And then you can derive this estimate explicitly in terms of real numbers, which is important for if you are interested in the final element error estimate. How does the error constant depend on the real number? That is important. And here is this is true if the epsilon satisfies this condition. It's not always true. At least that's the only case we can prove. And this looks pessimistic, but this constant gamma 0 depends on 1 over is the wavelength, 1 over k is wavelength, and then but there is also proportional to 1 over r. R is the diameter of d. In the computation, real computation, r is related to wavelength. So usually like a 20 wavelength. So therefore, this really is in practice is really the constant, pure constant. Okay. And a remark here is so the idea for the short wave pulsing is to use the Friedholm alternative principle because it's not a corrosive problem, but for the random case, and had to be careful to use this one because for this compactness you have to work harder, okay, to get it. Okay. So look at the algorithm, then you just write your solution in terms of power of epsilon. You plug in now just to show you exactly what is this squid error operator. It's nothing but Helmholtz as expected, but it's a deterministic Helmholtz. And the alpha disappear. Alpha is disappear, all the randomness goes to the right hand side. So each mode is satisfied as the same operator on the left hand side. That's exactly the framework says. Question?
An assumption on the random coefficient, whether it's bounded or the distribution of eta.
Eta is just generic.
There it says, no? On the right.
It's bounded, so it's not Gaussian.
Yeah.
So then you see
another question.
Oh, question?
So in these formulas, just now in this formula, you now set alpha 0 equal to 1 everywhere, yeah? Like you say here. So everything now below is alpha 0 equal 1.
Yeah, this is the for everything below alpha.
So
It's written alpha 0.
Oh, and this is for convenience, set alpha 0 equal to 1. You can carry alpha 0 everywhere. This is just assuming it's a constant. Yeah, actually, I think you can make this as alpha 0 x. As long as the independent of omega is good. And the satisfied elliptic condition.
next slide. Here all the alpha 0.
Yeah, but the 1. Otherwise, you have alpha x, alpha 0 x there. But the independent of omega, that's the key. Deterministic operator. Okay. So now you can see this is the example shows exactly what is operator squid error is. Then you choose our favorite discretization method solve discretize the Helmholtz operator. And actually here's the theory. If you cut for the first n terms, capped n terms, and it can be shown, and the convergence strongly in the energy space. And also have an error in the mean. Error is exact here is square, take a square root, and it's epsilon to nth power, yeah, as expected. Because you cut from next term is epsilon capital n power. It should be. Okay. And where the catch here, this convergence is proved under this assumption, and there's a sigma and related to epsilon with the wave number less than 1. Equivalently, epsilon is but the wavelength order, okay? And this condition is proved. And later I'll show you examples. What happens if this is not true? Well, numerically says sometimes working, sometimes does not work. And the theory is, in some sense, the theory is sharp. So the algorithm, repeat the algorithm, and you discretize your Helmholtz using the favorite method, and we choose the IPDG. And Anari is here and do the IPDG earlier and for the Helmholtz. And we did a list of Helmholtz and we improved it for the, in particular, considering of large wave numbers and specially designed the IPDG method, which worked better for the Helmholtz, for large wave number case. And you can replace this by your favorite method, discretize your Helmholtz. And you see your Steve's matrix A and then do the area U. You can do the block Krylov. And here we do the area U. And see then you repeat it using it and the backward and the forward substitution. Okay. For each mode and for each realization, repeat it using that. Okay. Then you form your approximate solution. And because you have all the realizations there, you can form any quantity of Stochastic interest you like, in particular mean. Then you get the approximation for the expected value.
Now this is the approximation, but what is the convergence? Is this series converging or is it just asymptotic form?
You mean the convergence in which sense? Let me just give you the next slide here. So in terms of which sense, if you fix epsilon, that is true, of course, it will converge by the IPDG method. And not only converge, but also the rate of converge. Explicitly depends on the wave number. And this is the Monte Carlo convergence order, half order. Then this is the epsilon nth power. Yeah. In this norm, in the energy norm, and here. And there's epsilon nth power. So in other sense, it could not converge. Okay.
But it's a formal asymptotic expansion. So how do you?
No, not the form. Not the form. Formal is for the idea, but it is proved. It is convergence energy norm. It's proved in the energy norm.
Ah, okay.
It's not a formal anymore.
Okay. Okay. That's the theory.
Yeah, it started with a formal idea, but you can think borrow the idea from homogenization, but it's proved. Yeah.
So can you go back? So this is interesting.
Which one?
The previous one.
Theorem.
Oh, theory. Oh, here.
This one.
Yes.
Yeah.
So because you need, so you need the sigma less than 1, sigma less than 1.
Yeah. So epsilon, there's a restriction on the side noise, strength noise. It's as expected, should relate to wavelength. Yeah. It's not a surprise.
So maybe I can ask my question that came before. It was too quick for me when you described the generalization via KL expansion. I didn't understand how you can.
That one is application specific. You have to go to the assuming something about your coefficient,
Okay.
like alpha. In the application, alpha has a Gaussian and has to relate to some kind of covariance function nicely in this form. Then you can do that.
Okay, so you use a sort of mean-based approach where you first use the first mode and then.
In that case, it's the mean based, yeah.
But you kind of hinted that in this Helmholtz thing, you're only doing the weak case, but you can't generalize or you cannot generalize.
You can generate in that special case. If your alpha is alpha and satisfy that kind of covariance function. The alpha is Gaussian, you assume that alpha is a Gaussian type.
But again, with the same assumption, same restrictions on the epsilon, same restrictions on the epsilon. You still can only have very small fluctuations around the mean.
Absolutely. Yeah.
But you also have a problem if it's Gaussian because you won't have the binder neither.
Yeah, exactly. That's the problem.
So it can't be.
Yeah. So this is you can prove it, and then computation show it may be different. You see what I mean? Can expand the boundary, but that's a proof you can show.
The Gaussian might not converge at all.
I'm sorry?
Take a Gaussian field might not converge at all.
May not be general Gaussian, may not.
General,
Yeah, if unless your covariance function is satisfied, it can be key property.
No, but even if it does.
I think it never converges.
No,
Anyway, so it's not for the area, of course.
it's not physical.
So that is the area estimate is here. In that sense, is converging. Yeah. So that is a application, for wave problem, because this community, a lot of people doing waves. I show this one, and then you can. By the way, for the computational complexity, where is CV? Then we can look at it. So suppose your domain have the capital K points. Your points is a capital K. So if you do the area U, then the computational complexity is 3/2 KQ. Okay. So then you do the many this backward forward substitution, which contributes to many computation, multiplication. Then you add up, that's it. And here, I'm telling you, I already told you the n number of modes usually be small. So let's ignore the n. You will see that the n is very small. And in practice, 3 or 4. Okay, so that get rid of n, so then you have mk. Remember, m is number of sapling. Okay. So it says if your number of sapling is less than square of the total grid points, that is a huge number. Of course, in practice, we never reach that high. So even in that worst case scenario, your total computational complexity is about solving for you, you know, and deterministic problem. Okay. So that is saving. So here is an example. I just show you one example. And indeed, this epsilon should depend on wave number. Epsilon should choose to, if you violate that condition, sometimes work, sometimes does not work. The theory proves under that such assumption. Okay. So this is the mesh, and this is the eta we choose. And then you see that this just shows you, and the 4, this is the relative error. And in terms of n number of n, how many modes we need with the epsilon, should have said, epsilon is 1 or k. K is 5. So then the case. So that in that situation, you only need about 4 modes. Good enough. Relative error is the error divided by the solution. Is the energy norm. Yeah, energy norm. Yeah. Okay. Just to show you that in practice, we only need a very few modes. In all the computations, practically, we only need very few modes. If epsilon small in particular, as expected. Okay. So this one is on a laptop, or no, in the desktop, which is just to give the relative comparison. The first line is says if you do the Monte Carlo directly, brute force Monte Carlo, it is not as good as we expected. You know, see with one magnitude of a computation. If you do the larger the problem, you see even more. Actually, that's the larger the problem, you see even more computation. Okay. So this is shows that you choose the more modes. How about what the cost? And then you use one mode and 2 mode, and then you see the how much computation time you add to it. Okay. And this example shows that you make this noise become stronger. The absolute is the strength of the noise. You make it larger. And in this case, is satisfy the assumption in the theory. If you continue to increase it, later this will be, I think, for the H, we violate and the condition. The algebra calculate violate the condition. This is the mean, computer mean solution. This is the one sample. Okay. And let's go to the graph. See here, for the H, and the same as that you have 3 modes, and the error is not good anymore. You want to say, oh, maybe I want to add more modes, see if it's improving. And it turns out, for the 8, it does not improve. And the means is epsilon is large, it's not converging. Please.
Uniform, not Gaussian, it's uniform. Eta.
Here. Yeah, but then you generate the Gaussian through the uniform noise. That's my understanding for my collaborator says. Okay, sorry for, I can talk to you later for that one. I think you use it uniform the noise to get a Gaussian.
I think your phone is not.
Oh, mine, I thought it's yours. Sorry. Okay, thank you. Yeah, okay, so we are good. So that is one example, just show you the framework and the works for the acoustic wave, Helmholtz. This can be done with the first application, and it can be done for elastical wave, similar, right? Exactly similar, but as a vector form. For the Maxwell, also the same. All the theory is similar. Of course, the vector form, you do the little bit harder work. Okay. Computationally, of course, is a much more intensive for compute. But all these papers you're interested in, all published papers a few years ago, you can look at it. And scattering by the rough surface in 2D, and we did that too, and use this, incorporate this idea into it for computation. And for random diffusion problems, this Helmholtz is not the coercive problem and indefinite problem. And then you can do the for the diffusion problems, which is in particular for application of material science. Okay? In fact, in last during the COVID time, we cannot travel. We work with some friends, collaborators, indeed using this idea, actually solving the stochastic homogenization problem. Okay, have you there? And here, I don't have time to talk about that, right? Here, I'm going to talk about the expansion, improving method. Make this the more, can apply to more general problems. Okay. So here is, let me, for those who are not familiar with the ensemble method, just a few couple slides, remind you what is ensemble method for parameter dependent problem. The idea, very simple, similar, relate to the multimode idea, but it's interesting. Okay. So suppose for modal problem, you have the heat equation, and then you have the multiple, many parameters. So parameter dependent problem, capital G parameters, you want to solve this problem. Of course, the brute force is you solve this G time, expensive. And the ensemble method said, how can we solve this more efficiently? In particular, to achieve efficiency by reusing computation. Not just solve for each parameter separately, but reuse computation as much as you can. Yesterday, there were a couple talks talked about the MOR, model order reduction. That's another approach. You reduce model, make the model simpler, then you achieve efficiency, see with the computation. Here is not. The idea is you don't change the model, same model, but you reuse computation. Reuse computation to to get the efficiency. So here's a very simple idea. One idea is you get the mean. The coefficient new J, you get the mean. Then you plug in each one in terms of new previously, right, this way. Now is the average left-hand side, and the other guy go to the right side. Now you can see left-hand side is a coefficient independent of the number of the parameters. So then you just do this time relaxations, then you get the iteration. So that's it. So it's very simple. Of course, this is just one way to do it. You can choose the mean. Also, you can choose maximum. In practice, you can choose the maximum among all the parameters, and you do the same rewriting, and you get this guy in the time. And so now the left-hand side operator is parameter independent. All the parameter dependence go to the right-hand side. Then you can reuse computation in the same idea. So those actually indeed was done by a lot of people. In particular, I was mentioned by the Bill Layton's group in the Pittsburgh. They do number stocks, parameter dependent number stocks. They use this idea, ensemble method, with the sequence of papers. My collaborators, they work on this heat equation and the related problem. Okay. So here, I want to show you how to combine these two methods, multimodal method and ensemble method. Because their idea is similar, reuse computation. Okay. So this is the generalized algorithm. And quickly, because our time is almost up. So the keyword, reuse computation. Don't change the model, not like the model reduction method, change the model to saving computation. Here is the same model, but the reuse computation as much as you can. This will be done on your solver level. So idea is very simple. So I present this in the general framework. You have the linear variation problem. The bilinear form A depends on parameter omega. Could be parameter, could be deterministic parameter, could be stochastic parameter. Omega could leave a probability space. Okay. So idea very simple. You choose A0. Choose, okay, we choose. Not like homogenization. You have to use the homogenized coefficient. No, we choose, as a user, we choose A0. How? Of course, this later, okay? So then you rewrite this A into this A1 and A0, and you just shift the A1 to the right side. Iterate, that's it. So algorithm is very simple. Iterate. Left-hand side operator now is independent of the parameter, omega. You can do the same trick. You do either block Krylov or LU and save it and repeat using the computation. Okay. And relation with the multimode is very simple. You can do this capital U and relate to little u by this relationship. So basically, capital U is a accumulation of the little u. Then you recover the multimode method. And now A0 is important. How to choose A0? Okay? Because this should be problem dependent. So here are a few guidelines. The A0 problem should be well posed because it's a variation problem. So the first condition says is well posed. And this is the more intensive, restrictive property. So the A1 term should be small. Small perturbation, meaning is called a relative dominance. A0 term should be dominant as expected. Okay. So here the rho is less than 1. Okay. So then they have a convergence. Convergence rate is a rho. Okay. You can, and this is just appeared in the paper this year actually. And then you can do the final element. The same thing, just discretize, and to final element, the same rate. Now you converge to the final element solution for global problem, and you compute this guy. Okay. So how to choose the A0? That's the key for the application. Again, expected is a problem dependent, should be. How to choose A0? And here they give 2 examples. One is a parameter dependent diffusion problem, and you have a sequence of the problem. And then you can choose, for example, you choose average. Then they give you A0. Using average coefficient, you get A0. Okay? And I see this. Now this A0 is not constant anymore. It's a variable function, but you depend on omega. That's the key. So that's one. You can do another one. You can do the maxima. Actually, it works sometimes. Which one works better? In practice, it depends your situation. Okay. There's one important trick is a mini patch, like learned from a stochastic gradient descent. Or you do the mini patch. You have the dependent parameter. So you have clusters, small clusters, then you do the average, maybe on a small clusters, you solve several small problems. We call the grouping technique. Works well in some problems. Okay. So I didn't put it here, but that is another technique to in practice. Next application is a random problem. Random problem. Now you have the omega now leaves in the probability space. You can approach one, which is like the multimodal method. If you have the weak media, then you do that. Just choose the mean as the E0. Then exactly recovers multimode method. But you don't have to do that way. You can treat it differently. Second approach, you do just choose your samples, GS samples. Then you have the reduce the problem into the parameter dependent problem. Then you can use the 2 techniques we introduced here to this problem. It turns out, for the random problem, this one works better. At least for the example we test. Okay. Just to quickly show you one simple example shows that indeed is the second trick has worked better. So this is a random problem, and then you have approach 1, and you can calculate for this particular problem the rho, the rho in the criteria for the A0. Rho is exactly equal to epsilon. Okay. So the convergence theory says rho has less than 1. If epsilon has less than 1 for convergence. And then the example shows exactly the case. You say, if you choose the rho, which is, epsilon is bigger than 1. Not a convergence, it's error. Rules, not a convergence anymore. Same problem, but I can do the second approach. I do the sampling first, choose the largest sample first. Then I treat the problem as a parameter dependent problem. Now I can choose epsilon larger, bigger than 1. Because the rho now is not the same as epsilon anymore. Rho now, even epsilon is 2, rho now is 0.5. So you still have theory guarantee of convergence. Indeed, it shows convergence. Okay, and so you can see this the error that decrease is converged. Okay, so this is the one, and here you can choose the A0 is the maximum or is the mean. Both works. Both keys works, but the key is you can choose for the problem with larger noise, because epsilon is the strength of noise, which is bigger than 1 now. You're using the multimodal method, not converging. But for using this second trick, and it doesn't converge. Okay. So, okay, the time is up. So summarize. So I show here is a quote-unquote framework to solving random problem. The keywords is reuse computation. Reuse computation, don't change the model, but reuse computation as much as you can. This will be done, it was done in the solver level, okay? And you can, I didn't say that how do you discretize the space part. And then for the wave problem, we use a DG. And then for the different problem, you can choose different your favorite method to do the space discretization. For the Monte Carlo part, you can do more tweaks. We just use the standard Monte Carlo. And you can do the more faster one, more fancy one. And in particular, multi-level Monte Carlo, easy to plug in, just do it. Indeed, we use this trick to solve nonlinear stochastic PDEs. When you discretize each time step, you have to solve it. Traditional way to do it is Newton. You do Newton, fine. But you can, now you need to solve a number of stocks, 500 times, maybe 1,000 times. That's too expensive. And then instead of doing that, we're using this as a solver to do that and make this more efficient. Okay. Indeed, we also use this trick to do the stochastic homogenization problem. That actually is the paper just recently appeared on the Simon's Journal of Scientific Computing. Thank you.